For decades, automotive engineering was highly decentralized. If a car needed a new feature, manufacturers simply bolted a brand new, isolated computer into the chassis. Today, modern software-defined vehicles do the exact opposite. They funnel everything into a single, centralized brain. Look at this system architecture model. To save physical space and weight, manufacturers consolidate what used to be dozens of distinct computers into a single processor. This creates a mixed ASIL environment, where experimental, low-stakes AI perception systems and high-stakes life-or-death systems, like braking and steering, are forced to share the exact same microchip. To prevent disasters in this shared space, engineers rely on a strict engineering rule called freedom from interference. It demands a hard barrier between systems. A bug or crash in the low-priority AI must never possess the ability to affect the high-priority brakes. Putting everything under one roof gives the vehicle the processing speed required for autonomous driving, but it also creates a systemic vulnerability. If that internal barrier is ever breached, a trivial glitch in a camera feed can compromise the entire vehicle. Imagine a self-driving car merging onto a highway at 60 miles an hour. Out of nowhere, it hits a localized torrential rainstorm, and a blinding sheet of mud completely coats the front grille. According to the vehicle's standard functional safety monitors, everything is fine. There are no short circuits, no severed wires, and no logical errors in the code. The hardware is operating exactly to its specifications. But look at this visualization of the optical sensor data. The AI is experiencing what engineers refer to as SOTIF, the safety of the intended functionality. The system isn't broken. It has simply hit the physical limitations of what its lenses can interpret. The crisp geometry of the rower has dissolved into a chaos of dots and noise. Because the AI is technically functioning perfectly, diligently trying to read a road it cannot see, the car's traditional safety alarms never trigger. That silence leaves the vehicle entirely exposed to a catastrophic chain reaction deep within its own circuitry. Faced with blurry, chaotic data, the perception AI goes into overdrive. It begins rapidly generating massive amounts of temporary calculations, entering a desperate guessing loop to determine if a gray shape is a shadow, a raindrop, or another vehicle. This chart displays the chip's shared processor capacity. As the AI frantically churns through the visual noise, its resource usage violently spikes. It monopolizes the processor and physically squeezes the braking system down to near zero capacity. The brakes are starved of the execution time they need to calculate their next move. The starvation quickly spreads. Shifting to the memory pathways, we see the AI flooding the internal buses with millions of useless data points about raindrops. It creates a dense traffic jam, physically blocking critical steering and braking commands from getting through to the main memory. By attempting to do its job under extreme conditions, the most intelligent part of the car's brain hoards the internal resources, inadvertently suffocating the systems keeping the passengers alive. The panic quickly escapes the microchip. Unsure of what it's seeing, the AI fires thousands of frantic, false positive hazard warnings down the central communication cables. Network engineers call this a babbling idiot failure. This diagram maps the car's internal network bus. The overactive AI node blasts endless messages across the shared line, maxing out the bandwidth. When the brakes try to send an emergency adjustment, the signal is discarded simply because there is no room left on the wire. A sudden change in the weather effectively forced the car's AI to launch an accidental denial of service attack against its own body. The strict rule of freedom from interference is broken, leaving the physical safety mechanisms paralyzed. We cannot program a car to control the weather. Instead, engineers build an automated, multi-layered defense system to strictly ration the computing power any single feature can consume. The first defense sits within the operating system. A software tool called a Watchdog manager constantly monitors the AI's execution time. If the AI exceeds its strict allowance because it got confused by mud, the Watchdog forcefully cuts its power to break the guessing loop. The second layer protects network cables. An Ingress policing switch identifies AI spam, bouncing packets into the void to keep lanes open for braking. Finally, silicon-level cache partitioning locks off VIP memory lanes. AI data is mathematically blocked, bouncing off the exterior wall. These three fortresses guarantee that even if the vehicle's perception algorithms completely lose their grip on reality, the vehicle's life-saving systems retain an untouchable domain to safely pull the car over. As the industry advances toward fully autonomous driving, safety standards are evolving. Guidelines like the upcoming ISO26262 Edition 3 acknowledge that ensuring a microchip won't short-circuit is no longer sufficient. Future systems are deploying advanced frameworks like Neurosymbolic AI, which apply rigid mathematical boundaries to restrict how neural networks behave when exposed to environmental chaos. Building a self-driving car requires teaching a computer to navigate our roads. Keeping passengers alive requires engineering an architecture that can survive its own mind when the world outside stops making sense.